yeah, so this is slightly more of a presentation on why the paper-based things are maybe not the best way to manage our protected areas. And I just have to acknowledge that this is not my work primarily. It's the work of my colleague and PhD candidate, Chad Cheney. And I have the unenviable task of trying to get through 5 PhD chapters in 12 minutes, and I do not anticipate time for questions. So, yeah. In Table Mountain, we've had alien species present for a very long time, and the Table Mountain National Park was declared in 1998 with one of the main aims being to consolidate the land under protection under a single management authority. So Julia may have been good at land grabbing, but I think we were even better, much to their disappointment, I think. Anyway, so this has been quite successful. We're able to manage a very large tract of land. But what is really interesting, if you look, this is now 20 years of alien clearing across Table Mountain National Park, and while the situation hasn't gotten worse, we haven't gotten any closer to moving all of our alien density into a rare class. There's still a good spread of aliens across all the density classes. So our question was, why is this the case after 20 years of intensive budgets and management? And we've got some really good data, and so Chad decided to do a PhD. Now, he was incredibly ambitious. Okay, this is only a portion of our study area. And what he did was he overlaid the entire national park with a grid, which you probably can't even see because those grid cells are so small. Every 150 meters, they had a plot. So that is, you know, some of you have presented 70 plots, 100 plots. We had 10,000, okay? 10,000 plots, which were hand-sampled by those poor people in the picture. They went through many, many mountain hiking boots. And, yeah, we haven't seen them since, actually. Yeah. But we have made good use of their data. So, yeah. What Chad did then with this fine quality data is he compared it to data sets that have been used in management, 2 data sets, which I'll show you, the Working for Water NBALs and a management data set that the protected area managers were in charge of. And then he also modeled, based on the exact location of the species currently, what would happen into the future under different levels of management effectiveness and different management strategies. And then he also looked at effects of scale to see what happens if you consider the fine scale data versus coarser scale data. So I'm going to try and take you through all of that in the next 10 minutes. Okay, so if we look at what data came out of this, the fine scale data in comparison to Working for Water data and protected area management data, unsurprisingly, we found orders of magnitude more species in the systematic sample. But what is quite surprising is that even with this fine scale sampling, our curve didn't reach an asymptote, so there are more out there. In terms of what we're treating, it's less than 10% of the species that are out there are actually being managed. It gets scarier. If we look at the density estimates, so these are the management data density estimates. The scales are not consistent between the graphs, just take note of that. But they consistently, for all species, massively overestimated the density. So this is the systematic sample, much, much lower densities if you look at actual individuals on the ground. The Working for Water data was slightly better in this regard, but still some areas where it's orders of magnitude out of scale. And this was particularly bad for species like Acacia saligna, which are the more common species. They did much better for the species which are rarer in the landscape in any case. But this is really important because the densities are used to estimate the workload and as such the budget. And if you get it wrong, you're just paying tons and tons of money to work that isn't actually there. So just keep that in your mind for later. Okay, so the next thing we did using the same fine scale data set was to model how long it would take to clear the plants. So we did this in 4 stages. The first stage of Chad's model looked at just clearing. If we ignore all ecological processes and just look at the plants that are currently there, how long would it take to clear them, and what is the impact of declining management efficiency? So we defined management efficacy as the probability that each plant present in the management unit would be treated correctly, so killed and with the right kinds of chemicals or whatever methodology is required. The next phase of the model added the seed bank to the system. So if you allow the seed bank to germinate, how much extra work does that create? We then added fire. So fire obviously stimulates further seeds germinating. And this is all just to do now with the acacia species for this component of the study. And then the full model included the plants that are currently there dropping seeds every year, which is quite significant. So if we look at the results, so over a 50-year period for which the model was run, we've got a maximum average allocation of about 200,000 person days. So if we just had to clear the current standing plants, it would take about 2 years if we got every one first time. If you miss a few, so the MPE is the current measured project efficiency, I think it was something like 10 times the amount of time it would take to clear just those standing plants. If you add the seed bank to the situation, it gets 4 times worse. If you add fire, we expected it to get a lot worse. It actually didn't get that much worse. But if you add the fact that anything that you leave in the field is allowed to produce seeds, each individual is capable of producing 4,000 seeds a year, the situation becomes the stalemate that we see ourselves in, where you use your full person day allocation in perpetuity for 50 years and you are never making any gains. What we also saw is that this relationship is non-linear. So every percentage that you drop in efficiency below 80%, the situation is getting worse. You're leading towards getting to a worse situation than you were before you started management. But on the positive side, every little bit of improvement above 80% gets you closer and closer to be able to reduce the problem. Okay, so then we took the same data set with the aim of now reducing our acacias to being rare in the landscape, and we tested several management strategies from the literature. We also looked at, so this is now where you decide to prioritize which areas you're going to do first. I don't have time to go into the details of this, so I'm just going to put the results straight on top of the wording. It's not great, but anyway. The keep it clean strategy, where you focus on lightly invaded areas, was able to clean the most hectares, but it did the worst in terms of getting hectares into a maintenance state. So you could clean large areas of light infestation, but overall your protected area remained more invaded. The best strategy under current efficiency was the consensus strategy that looked at post-fire clearing, low density, and high altitude. But if you're able to improve your effectiveness and implementation in field, then actually a follow-up strategy would be better. So then we also looked at how each of these strategies, in combination with effectiveness, impact on your ability to reduce your return interval. So that is, if you clear a site 1 year, you should get back there within 2 years and clear it again. The best in this regard was the keep it clean strategy, where you're just targeting the low frequency areas, so you're able to revisit your sites very often. And the worst, kind of what you would expect, was the water strategy, where you keep going for the same areas and you have a very low repeat frequency. What was quite upsetting was that the historical distribution of frequency visits to sites wasn't actually very good. So we were not reaching our areas within that 2-year period that we would like to see. So why is this important? Well, if you have a fire, for example, that's what it looks like 2 months after the fire, 6 months after the fire, so what? 15 months after the fire, you've got this mess. And if you leave it for 9 more months, that mess will be making more seeds at 4,000 seeds per individual. So it's really, really critical that you meet those return times. Okay, so then this is where things get really complicated. We try to look at how effects of scale and range properties of a species impact on our approach to clearing them. So this is an approach proposed by Melody McGeoch and her colleague, where they viewed an alien species as being on a trajectory from being uncommon in the landscape to becoming common. So the more common you are, the more widespread, the larger your population size, and the more even the distribution. So we adapted this slightly. We used 3 metrics. So this diagram has 3 axes. It's kind of, you have to use your mind a little bit. But basically, there's 3 metrics: novel population, novel range from narrow to wide, where you're looking at the occupancy of cells at different grains. And I'm not going to explain it in any detail because there's not time. You just have to believe me. And then we've got small and large population size on the bottom axis. And then across here, we looked at how clumped the distribution was, assuming that a clump distribution would indicate a recently established, so time from invasion is recent, and a more even distribution would represent a later stage of invasion. Okay, now the important thing is that going through to the results, you can use these to assign each species to one of these cells based on those 3 factors that we're going to measure. And there's an appropriate management strategy. If a species has a particular range structure, for example, if it falls into that newly established category, you might want a rapid response strategy. If it falls into the blue blocks, a control plan where you aim to reduce population size. The orange and red, you aim to limit expansion, so that's a containment strategy. On this side, we've got a maintenance strategy where you've got a dispersed population and you're aiming to reduce its range. And then if the species is not present at all, you can follow a reconnaissance strategy. So what we did was we calculated these 3 metrics at 6 different scales across the protected area. And then we looked at how the species range properties change as you go at coarser resolutions of looking at the problem. So it resulted in some really cool results. Basically, for each species at each scale, you can draw one of these little plots, and you can see, so for example, Acacia saligna at the finest scale had most of the species in this newly established range, for which the most appropriate management strategy, for example, would be the early detection rapid response. And then we plotted it on a tree. So each one of those little points around the edge is an actual site in the national park, and you can tell at that site what type of range properties a species has. So if you look at this in some more detail, we found 3 main patterns. So for rarer species, for example, this Paracerianthus, you can see that in that one arm of the national park, remembering that each of those is a site, and as you move into the middle of the diagram, you're getting coarser and coarser scale, with the whole park being represented by the root node, you can see that there are just 2 sites that are invaded next to a whole bunch of clear sites. So if you just go to those 2 sites, you can remove that species from that entire portion of the national park. We also saw that there's some species that have low-density sites in proximity to high-density sites, and some species for which a range of strategies would be appropriate at scales very close to one another, and that there are different strategies represented at different scales. So you need to be really careful in being open to different strategies at different scales. I don't have much time left, so I'm just going to tell you 2 more things. The one is that there was one species, there was only one, for which we found the root node to be in this newly established block. So that species is prime for eradication from the park, because even at the coarsest scale, it's got that range property of looking like a newly established species. Right, and then the important thing is, what have we done with all this information? Now, because we work for the national park, we're able to immediately integrate this back into management, which we've already started doing, and we've got some really cool results. So what Chad has done is he's got the annual repeat monitoring to inform the person day allocation. So every year they go out and do a sample of those 10,000 plots to inform the working for water data. And then everyone was very worried that because we are estimating such low densities, that we might not have enough work, because it's a job creation program as well. But these fears have been allayed. Because we've got much longer species lists, we actually have more person days than we had before. We now know that we're not very efficient, and one of the things that's being done is that the allocation of budget towards training has doubled since 2016, so putting more effort into making sure that people do things right. We've started an early detection rapid response program in 2016. It was formalized in 2017, and the budget for that is growing annually. And then, very importantly, in 2017 and 2018, they planned such that they would reach all sites within a 21-month period, and I have it on authority that that was actually achieved, which is fantastic. But the improved workload quantification has resulted in teams not being able to complete their tasks. So that order of magnitude difference that we measured in density estimates, we said, right, well, there's actually much less work. You're going to get much less money. 50% of the work now cannot be done. So one of 2 things here. Either we need to revisit those norms and standards. Are those targets actually achievable? And to recalibrate how we do this. And we probably also need some work into the factors that play a role that could be improved. So the social dynamic of the team, the job security of the people in the field, and so on. Yeah, that's probably all I have time for now. So firstly, thank you to the mappers, and to Chad, who couldn't be here today because he's busy writing up his thesis to hand in at the end of the month. Yeah, thank you.